Welcome students to this video, and in this part we are going to do something called a periodic linear systems. Yes, so what does it mean? So let us consider this problem. Consider x prime equals to at times x, this problem. Yes, and let us assume that it passes through x naught at the point t equals to 0, the curve. Now you see, by Picard's existence and uniqueness theorem, we have already looked at this problem, right? That if A is continuous, so if A is continuous, what does it mean? It means that all entries of the matrix A are continuous. Yes, in whatever interval I, some interval I, then you have the existence of a global solution, right? So there exists a solution which satisfies the equation for all t in I. So there exists x here satisfying the problem. Let us put this problem as p for all t in I, of course, which contains 0 here. So that is always there. Now the thing is this, so this is fine, but if at, now see, for at equals to t, yes, if at is identically equals to A, let's say, so that's a constant matrix, yes, constant matrix, then we know that this solution will be given by x of t is nothing but e power at times x naught. Yes, but this is not true. So please remember, this is not true in case of variable coefficient, right? Variable coefficient. But the thing is, so can we say something more if you have a variable coefficient problem? That's the question. Yeah. So what we are going to do now is to see, we are going to, for this problem, for this video, we are going to consider, so we are going to consider a much more general problem. Okay, going to consider the problem x prime equals to at. Clear? So A is a variable coefficient matrix, n cross n matrix, plus b of t. Is this okay? Right. So this is the problem which we are working with, and let's call this problem as p prime. Clear? Where we will assume that A and B have continuous entries, in some interval. Yes, continuous entries in some interval I. So all the entries are continuous. That is what we are assuming here. Now the thing is this, the question is this, we know that there is a solution, right? We know that there is a solution for all t in I. That is fine. Yes, but the problem is this, if you put some more conditions on at, so if one imposes more conditions on A and B, can we derive something more? Is this okay? So what I'm trying to say is this, can we say something more about the solution if we put more conditions on the coefficients? Of course we that's just our hope, right? That if we put some more conditions on AT, some nicer conditions on AT and BT, then of course we hope that the solution will also reflect that generosity, right? So okay. So what we are going to do here is, we are going to look at linear systems which are periodic. I'm going to explain to you what all of this means. So essentially, first of all, we start with the definition. What is the definition? So this we will put it this way: a function y of x, clear? Some function y of x is called periodic, Yes, of period let's say W positive. Okay, if for all x in the domain, whatever the domain of y is, yes, for all x, y of x plus W equals to y of x. Clear? Okay. So geometrically what it means is the graph of yx repeats itself in successive intervals of length W. That's what it means. Clear? Okay. So it is basically repeating itself. And as an example, of course, you guys know that sines, cosines, there are like periodic functions. And what is the period? 2 pi. Okay. So for example, we know that sine of x, cosine of x. Yes. See, I am writing here x. Don't get confused, or maybe I think it is better to put it this way. So let me just change the definition a little bit. Let me write it as y of t. Yeah. So you should don't get confused. That's why. Otherwise, it's not a problem. Everything is same. So sine of t, let's say, or cosine of t, they are all 2 pi periodic, right? Okay. So what does it mean? It means the sine of x plus 2 pi is nothing going but sine of x. Again, cosine of 2 pi plus x is also going to be cosine of x, right? Fine. Now you see, the thing is this, and of course we are going to assume. So you do realize that this W is not unique, right? Okay. So what we are going to do is, for now, for our convenience, we are going to choose the W as the smallest possible such number for which this holds. Here, okay. So that is what we are going to call that this thing, the period. Now the thing is this. Let's say if each component, okay. So this is kind of a remark 1. Let's just put it. If each component xi of t, okay, 1 less than I less than n, here, of x of t, and each entry aij, okay, of t for 1 less than I j between n, clear, of the matrix A, clear, are periodic of period 2 pi, of period W. Is this okay? Then x of t and a of x, a of t, clear, are said to be periodic of period W. Is this okay? So essentially what I mean by this is, you see, let's say A is a matrix, right, and it depends on T. Essentially, you see, A matrix has all these entries, and all these entries depends on T. So if for every entry is a function of T. So as a function of T, if that is basically periodic of some same period, the period has to be same W. And again, the solution, let's say the function which you are talking about, the unknown function x of t, that is also like all the components are like periodic functions. Then we say that basically those are periodic of period W. That's just what you understand by period. Okay. Now you see, periodicity is a very, very important aspect of study. Yes, why? Because if you think about it properly, you see, what does ODE do when we study a system, or when we study an equation? Essentially what we are trying to do is we are trying to model a situation, right? So that's the thing, model physical situations. Now if you think about it carefully, most physical situations which we deal with are generally periodic. So for example, let's say the motion of planets, or sun, moon, whatever, right? The motion of planets, or let's say in biology, our heartbeat, yes, heartbeat, or let's say the growth of our hair, let's say, yes. So as you understand, most biological features, or the let's say space science also, motions of planets, okay, or pendulums and all these motions are generally periodic motions, clear? Okay, so it is actually makes sense to study the periodic systems, okay, and that's the idea of studying this. Okay, so first of all we are going to do this theorem. It's called the necessary and sufficient condition and sufficient conditions for p prime. Clear? What is p prime? X prime equals to at times x plus b of t. Clear? P prime to admit periodic solution, okay, and I will put it like this: W periodic solution. What does this means? It means that it has a periodic solution of period W, right? W periodic solution. So let us give you the necessary and sufficient condition for this thing to happen. Here, so first of all, this theorem. What is the theorem says? It says that let the matrix A of t and B of t, okay, are continuous and W periodic. Okay, I hope you understand what this means. It means that let's say A is a matrix, n cross n matrix, right? So all the entries are essentially a function of t. They should be continuous and W periodic, and the same holds for B also. It's a n cross 1 matrix, and for that every entry has to be continuous and W periodic. Clear? In R, let's say. Clear? Then P prime. Here this P prime, this problem P prime x prime equals to at times x plus bt has a periodic solution, x of t has a W periodic solution. Let us put it this way: has a W periodic solution x of t if and only if x of 0 equals to x of W. Is this okay? That's the theorem. So essentially what it is saying is this, very simple. See, think about it this way. Let's say P prime is this equation, right? X prime equals to at times x plus B of t. Yes, if A is periodic, B is periodic, you expect your solution to be periodic, right? Kind of, yes. So that is what is happening here. So it's saying that if you have a solution, okay, W periodic solution. So basically what it is saying is this: if you have a W periodic solution, of course this is happening. You see, this is the definition of periodicity. X of 0 has to be x of W, right? So there is nothing to prove here. But the other part is also true. So what it is saying is this: if x of 0 equals to x of W, if you can show just for 2 points, just the 2 points, yes, the curve is closed essentially. So basically what you are showing is this: you are basically looking at the curve, right, and you are showing that the curve is closed. So basically at the point t equals to 0 and at the point t equals to W, the curve comes back to itself. If that happens, so if you have a closed curve, then the solution is going to be periodic. That is the that is what you expect, right? So if you have a solution which is like a closed curve, so what happens? It will again go on doing the same thing, right? So basically it is going to be periodic. So that's the idea essentially. Okay, if you have the system is periodic, so basically A and B are W periodic, then the solution which you are going to get, yeah, you will be W periodic if and only if x0 equals to xw. Okay, so let's look at the proof. Of course, if x0 equals to, you see, if it is the W periodic solution, you see, if x is W periodic, let's say, yes, periodic. Then x of t plus w equals to x of t for all t, right? So therefore for t equals to 0 also it is true, and hence x of w equals to x of 0. So that's just trivial, right? Okay. So conversely, now the important part, conversely, what happens is this. Let's say let x of t be the solution of p prime. Is this okay? Yes, and satisfying x0 equals to xw. Is this okay? See, now we are assuming that x is a closed. So essentially at the point 0 and at the point w, it is basically the same. Yes. Then we are going to show that if it is a solution, it has to be w periodic, right? Yeah. Okay. So to do that, what happens is, if we define v of t is nothing but y of t, sorry, let me put it like y of t, it will be much better to put it this way, x of t plus w. If we define it like this, then that will imply, you see, since x is a solution of this problem, then y also solves this problem. See, y prime of t is nothing but x prime of t plus w. Clear? This is just a chain rule, right? Chain rule. Now, if this is the case, and what is x prime of t plus w? It is nothing but a of t plus w and then x of t plus w plus b of t plus w. I hope this is clear. Yes. See, if x is a solution of the problem, so it satisfies the equation for all points, right, in the interval. So basically this is t plus w is some point, right? So we can just substitute by t plus w. Now you see, this is what this implies is, since a and b, they are, you know, w periodic. It is given, you see, a and b are w periodic. So a of t plus w is nothing but a of t. And what is x plus t, x of t plus w? It is nothing but, by definition, it is y of t. So it is y of t. Plus, what is b of t plus w? Again, it is b of t. That is just the given. Okay. Since a and b are w periodic, this happens. So you see, you have a problem such that, so therefore, what does y do? Y prime of t equals to at times y of t plus bt. Clear? And moreover, y at the point 0, what is it? It is x at the point w, right? And x at the point w is given to be x at the point 0. So that is what we started out with, right? So it is x at the point 0. So you see, y and x both satisfy the exact same equation, right? Yes. See, note, x and y satisfies the exact same equation, satisfies p prime, that is, exact same equation means p prime, satisfies p prime, and at the point 0, x equals to x and y are essentially same. Okay, what does that imply? Then, of course, since the solution is going to be unique, then it implies x of t has to be equals to y of t. There is no other way, and that will imply, what is y of t? It is nothing but x of t plus w. So this should hold for all t, right? In whatever interval it is, this should hold for all t. So that implies that x is w periodic. I hope this is clear. Okay. So you see, you do not have to worry about periodicity. So once you have the coefficients of periodic, you just have to check that there are 2 points 0 and w. Yes, if x, are same, x basically achieves the same value at the point 0 and w, then you have a periodic solution of exactly that w periodic solution. Clear? Okay. So now we are going to look at a corollary of this theorem. So let a of t be continuous and w periodic. continuous and W periodic. W periodic in R. Clear? Further, let phi of t be the fundamental matrix Fm. So basically it means it's a fundamental matrix, okay, of x prime equals to at times x. Clear? Then p prime has, sorry, not p prime, this problem, x prime equals to at times x, okay, has a non-trivial periodic solution, okay. Actually W periodic, I should write it as a non-trivial W periodic solution. Let me put it this way, W periodic solution x of t if and only if determinant of x of 0 minus x of w is 0. Is this okay? Yes. So basically what it is saying is this: if you have a periodic system, so for now if A and B are periodic, let's just call those systems as periodic system. This is a corollary, and this corollary is not about the inhomogeneous problem but for a homogeneous problem. So basically let's say x prime equals to at times x is the equation given to us, right? The homogeneous problem, that is, and you have a fundamental solution psi of t corresponding to that. Now you see what it is saying is this equation, of course 0 is always the solution of this homogeneous equation, that is given, but the thing is you can also have a non-trivial solution, yes, and the solution will be periodic also if and only if the determinant of x0 minus xw, the fundamental solution, evaluated at 0 and evaluated at w, you look at that matrix, if you take the determinant of that matrix, that has to be 0. Yes. Now this looks a little complicated, but the proof is extremely easy. Let's look at the proof of that. Proof. See, the thing is, for this problem, the general solution of x prime equals to at times x is given by xg, let's call it the general solution, is nothing but, if you remember, it is psi of t times, psi is a n cross n matrix, right, fundamental matrix, times as a constant c, and this c is a n cross 1 constant matrix, okay. Now you see, what do we need to do? If this solution, if one of this solution is a W periodic solution, yes, so see, if let's say x of t, xg of t is W periodic for some particular constant, yes, for some constant essentially, okay, is W periodic. Of course, that will give you if and only if condition, right? What is if and only if condition? If phi of 0 times c equals to phi of w times c. Okay, this is always true. Why it is true? Because of the earlier problem. You see, if this, in this problem, if you take b to be 0, essentially it is saying there is a W periodic solution. Problem has a W periodic solution if and only if x0 equals to xw, right? So this problem has a W periodic solution. Okay, so let's say x is a W periodic solution. That's the general solution, but there is a W periodic solution if and only if x of t equals to x of w. X of t has to be x of w. Okay, and that will imply phi 0 times c is phi w times c. Yes, yes. What does that imply? That will imply the system phi 0 minus phi w, okay, times c is equals to 0 has a non-trivial solution. Non-trivial solution. Is this okay? Yeah. Why is this true? Because you see, this w periodic solution which you have, this is non-trivial, we are assuming, non-trivial. Okay, so this system must have phi 0 c minus phi w c. That system has to have a non-trivial solution. Clear? Otherwise this is going to be 0, right? Okay, so it has to have a non-trivial solution. But for this system to have a non-trivial solution, what is the requirement? That will imply that, so it is both if and only if actually, that will imply the determinant of psi of 0 minus psi of w has to be 0. Otherwise this system cannot have a non-trivial solution. That's just the basic system of linear equation stuff, right? If this system, the determinant is non-zero, then this system has a unique solution, right? This system will have a unique solution, and the unique solution will be given by c equals to 0. Yeah, but since the system has a non-trivial solution, yes, c not equals to 0 essentially. So basically, there is one entry which is non-zero. So hence this has to be true. Is this okay? So what did we prove? We proved that the homogeneous system, please remember this thing, this is for a homogeneous problem. The homogeneous system admits a non-trivial w periodic solution xt if and only if the determinant of x0 minus xw is going to be 0. I hope this is clear to you. Okay, now let's look at another corollary. So let's say this is corollary 1, let's look at the corollary 2. So what is it? It says that, let's say that a and b are continuous. So let a of t and b of t are continuous and w periodic. Continuous and w periodic. Periodic in R. This is what we are assuming. Yes. Then p prime, the problem p prime, this problem, what is it? P prime is, where is the p prime? P prime, x prime equals to 80 times x plus bt. Yes, this problem has a unique periodic solution. Unique periodic solution. Solution, okay? W periodic solution. W periodic solution if and only if x prime equals to 80 times x, okay, does not have a periodic solution other than the trivial solution. Okay, so if this if x prime equals to 80 times x does not have a periodic solution, w periodic solution, okay, does not have a w periodic solution, other than the trivial solution. The trivial solution. Okay, so it's a beautiful corollary actually. See, what it is saying is this. Yeah, we want to know that if you have a w periodic solution which is unique for the system, right? You have an inhomogeneous system and we want to see whether there is a unique w periodic solution. What you can actually prove is it's an if and only if condition. That if the homogeneous system does not have a w periodic, of course you see the homogeneous system has the trivial solution which is always w periodic or any periodic for that matter, right? So that's not a problem. But the thing is, if it does not have a non-trivial w periodic solution, yes, then the original equation, the inhomogeneous problem, has a unique w periodic solution. Okay, so this type of properties are called Freedom alternatives. Freedom alternatives. Okay, so it's a beautiful theorem, right? It says that not, you see, this is kind of random alternative, not exactly, but kind of, you can think of it like this. See, what it says is this, please understand this. X prime equals to 80 times x has always a trivial solution. You don't have to worry about it, and that is always periodic. What it is saying is this: if you can show that there is no other periodic solution other than the trivial solution for this homogeneous problem, then you can guarantee that the original inhomogeneous problem has a unique W periodic solution. Okay, beautiful theorem. So you don't have to see, if you have to say something about the inhomogeneous problem, you don't have to study the inhomogeneous problem, you study the homogeneous problem. And if you can somehow guarantee that there is no W periodic solution, you can guarantee that there is a unique W periodic solution for the inhomogeneous problem. Okay, so the proof, maybe I can do it in the next page. So proof. So let's say that let phi of t, yes, be the fundamental matrix, of the equation x prime equals to 80 times x. Is this okay? Now you see, you remember, if this is the fundamental matrix, then by Duhamel's principle, we have proved this. Yes, Duhamel's principle. What do we have? We have that x of t for the inhomogeneous problem. So x satisfies the inhomogeneous problem now. Xi is a solution of homogeneous problem is given by the solution of the homogeneous problem, which is psi t times a constant matrix C, n cross 1 matrix, constant, plus this part t naught. So I am taking it from the, so let's say 0 to t psi of t psi inverse of s b of s ds. Yes, that is Duhamel's principle. Or I am not quite sure whether I told you that this is Duhamel's principle or not. Essentially, I think we called it a variation of parameter. Okay, this is basically variation of parameter, but the principle is called Duhamel's principle. Okay, variation of parameter formula. Yeah. Okay, so we have this this particular function is a solution of p prime, right? Yes, in terms of the fundamental matrix. Now see that if this xi, okay, xi of t is W periodic, when is this W periodic? That's the question. See, xi of t is W periodic if and only if you remember x at the point 0, xi at the point 0 equals to, sorry, xi at the point W. Is this okay? So what does that imply? That will imply, okay, that phi of c, see what is xi at the point 0? It is phi of 0 times c, and here if you put 0, this term is not there. So this is equals to phi at the point W times c plus 0 to W phi at the point W, phi inverse at the point S, b of S ds. That's what we are going to get, right? Okay, so that's an if and only condition again. Now, and what does that imply? That will imply if and only phi of 0 minus phi of W. That's a system, right? That's a system of linear equation. This is nothing but this phi of W, phi inverse of S, b of S ds. Is this okay? Now you see, the thing is, this system has a unique solution C, right? See, for this thing to happen, this has a unique solution C. Yes, has a unique solution, C. Okay, but for this system to have a unique solution, you need the determinant to be non-zero, right? But for that to happen, determinant of phi 0 minus phi W, that has to be non-zero. Is this okay? So Now, of course, the theorem holds. See, the theorem says that if this does not have a W periodic solution, then P prime has a unique solution, right? Okay. So you see, the thing is, we use this. See, determinant of phi 0 minus phi w is 0. If this happens, then there is a non-trivial W periodic solution of this system. Is this okay? What we showed is determinant in this, for this problem, determinant of psi 0 minus psi w is not 0. Is this okay? Yes. And the thing is, since this is non-zero, that will imply that the homogeneous equation doesn't have a non-trivial W periodic solution. Yes. So you see, this is an infernal if condition. So x prime equals to 80 times x does not have a W periodic solution. So basically, if it has a unique if the P prime has a unique solution, W periodic solution, yes, then determinant of psi 0 minus psi of w has to be non-zero. Is this okay? I think this is quite clear here. Fine. So now what we are going to do is very important. This theorem, yes, will actually we can use a lot this theorem, and for our purposes, for studying various differential equations, this theorem is called the Floquet theorem. Floquet theorem. Okay, I will give you an application of Floquet theorem also. We'll see why Floquet theorem is so much important. Okay, so let's say that, let us consider again, let A of t and B of t are continuous and W periodic. That is given, continuous and W periodic in R. W periodic in R. Is this okay? Okay. Then the following holds. Okay. What is it? Number one, the matrix, let's call it pi of t, okay, which is defined by psi of t plus w, here, is also a fundamental matrix, of the system x prime equals to 80 times x. Is this okay? And 2, there exists, this is important, okay. So first of all, what am I saying? I am saying that if phi of t is a fundamental matrix, phi of t plus w, that is also going to be a fundamental matrix of the same system. Clear? Also, you will have a periodic non-singular matrix P, non-singular matrix P of t, okay, of period w, clear, and a constant matrix R, such that, you see, this phi of t, right, the fundamental matrix phi of t can be written as P of t times e power RT. Is this okay? So what we are saying is this, see, that you can actually break down the fundamental matrix. Okay, see, the first part actually we need it for the second part, that's why we just wrote the first part. It's not very special. The second part is the special part. It says that any fundamental matrix phi of t, clear? So you understand what is your system given, x prime equals to 80 times x plus bt. This is the system given to you, clear? And what it is saying is this, if this is continuous and W periodic, this is also continuous and W periodic, clear? If that happens, then the fundamental matrix of the which system, the homogeneous system, can be written as phi of t looks like P of t plus, okay, one thing, you don't need b here, sorry, you don't need b here. Yes, why am I writing b here? It doesn't need to have any b. Okay, Let me put it this way. We don't need to have B continuous. Clear? Okay. What it is saying is you can actually write the fundamental matrix phi of t as P of t times exponential R t. Is it okay? Exponential R t. So you see, what is the proof? And what is the speciality of P of t? P of t will be a periodic matrix, W periodic matrix, and R will be a constant matrix. So you can write it as e power R t, which is like a constant matrix times t. So basically you can calculate e power R t, and then P of t will be a non-singular matrix which is periodic, W periodic. Okay. So what is the proof? So since phi of t, okay, is a fundamental matrix, of the differential equation x prime equals to at times x, right? That's what we are assuming. Then that will imply that phi prime of t, it will satisfy the matrix differential equation. You remember that, right? So one second, sorry, yeah, phi of t will look like 80 times phi of t. Okay, please remember this is matrix differential equation, not your usual one. Matrix differential equation. Okay, see, phi prime t is also a bunch of matrix entries, okay, which is a n cross n matrix, and A is a n cross n, phi is n cross n. So basically both sides is a n cross n matrix. This is a matrix differential equation, not your usual one. Please remember that. Clear? Okay, now you see what happens to p prime, and let's look at what is pi prime of t. See, if it is a fundamental matrix, yes, then pi will satisfy the equation, right? So what is pi prime of t? It is nothing but phi prime of t plus w, right? Chain rule, and which is nothing but a of t plus w. You see, phi is a fundamental matrix, right? So it satisfies the fundamental matrix differential equation. So this works for all t. So it works for t plus w also. So we just replace it by t plus w. Clear? Now you see, if A is w periodic, then A of t plus w is nothing but A of t. And what is phi of t plus w? It is nothing but pi of t. Okay. So pi is another matrix which satisfies the matrix differential equation. Yes. The homogeneous equation, that is. Yeah. And of course, the determinant of pi t is nothing but the determinant of this matrix, right? Psi of t plus w. Yeah, and that is of course going to be non-zero for all t. Yeah, it's a fundamental matrix, right? It has to be non-zero. Clear? Okay. So what we have is therefore pi is a fundamental matrix. Of the homogeneous problem, x prime equals to at times x. I hope this is clear now. Okay, now the second part, and this is the important part. Yes, how do you find, see what the second part is saying is, this is important in this saying. We can actually break the fundamental matrix in terms of a non-singular periodic matrix and then an exponential part. Yes, okay, so how do you do something like this? So let's look at it. Okay, so for the second part, part 2. Okay, see, the thing is, since phi of t and phi of t plus w, okay, this is what? This is pi of t, right? So they are both fundamental matrices. I hope you remember the properties of fundamental matrices. Then phi of t plus w can be written as phi of t times a c for some constant c. C is a non-singular constant matrix. Is this okay? See, again, please remember this thing. We proved when we talked about fundamental matrices, we said that any fundamental matrix, C, if phi is a fundamental matrix, phi t times c is also a fundamental matrix, where c is a non-singular constant matrix, right? And we also showed that any fundamental matrix, doesn't really matter, but any fundamental matrix will look like phi t times c. There is no other way. So since phi of t plus w is a fundamental matrix, so phi of t plus w can be written as phi of t times c. Is it okay? Now you see what we are going to do is this. This C is a non-singular constant matrix, right? So now we will do is this. Then there exists a constant matrix R such that C is non-singular, right? So C can be written as e power RW. What is W? W is the period. Okay. C is a constant matrix, so we can write it as a exponential of RW. This can always be done. Yes. If you are not convinced, you just please do it yourself. Yes. So and probably I am going to put it as a part of assignment. So that is there. Clear. So what we are going to say is this: C is a non-singular matrix, right? So what you can do is, if you have a non-singular constant matrix, then you can always have a constant matrix R such that C can be written as e power R, and here that W is some number, so it's not a problem, it's just a real number. Okay, so we can just put W there. Clear? So this theorem says that if you have a non-singular matrix, then there exists another matrix R such that the non-singular matrix C can be written as the exponential of this given matrix. Okay, right. So now once this is true, therefore what do we have is this: C phi of t plus w is nothing but phi of t times C. What is C? It is e power R w. Is this okay? Now we define a new function. Which is p of t. This is a matrix, matrix function, that is, and it is defined is like this. This psi of t, fundamental matrix psi of t, then e to the power minus rt. Is this okay? This is how we define it. Yeah, this is just a trick, nothing special here. Okay, we just want to put it in that form, that is why this is just a trick. So we define a new function p of t, of course it's a matrix, which is given by phi of t times exponential minus rt. You can do that. Therefore, you see, what is p of t plus w? Let's look at it. What is p of t plus w? It is nothing but psi of t plus w e to the power minus r t plus w. Okay, we can of course write it, and what happens is this: see, this is nothing but psi of t plus w is psi of t times c, right? So this is psi of t times c is nothing but e power rw, right? And this is nothing but e power minus rt times e to the power minus rw. Clear? We can write it like this. Why? Because you can actually see that they are going to commute, so we can write it like this. And then this is nothing but phi of t times e to the power minus rt. Is this okay? And then this is nothing but p of t. Clear? So you see, this matrix, the matrix which you define p of t, which is phi of t times e power minus rt, that is actually w period. Therefore, hence p of t is w period. Clear? Now, of course, phi is non-zero, exponential, that is non-zero. So determinant of p of t, that is also non-zero. It has to be, because phi is a fundamental matrix, the determinant is non-zero. Exponential, the determinant is of course going to be non-zero. So determinant of AB is determinant of A times determinant of P, so it's non-zero, right? So we can just write it like this. Clear? Okay. So the beautiful part about this is, once this is done, you see, then phi of t can be written as p of t times e power rt. Okay. So hence we proved our, see, phi of t can be written as p of t times e power rt. Hence we proved our theorem. Clear? Now the thing, this is the important part. Okay. Why are we suddenly interested in this? And that's the beauty here. See, the thing is, sometimes what happens is this: you can actually reduce. Okay. So this theorem, the above theorem, remark, let me put it as a small remark. The above theorem may help us in some circumstances, in some situations, that is, to solve the system, okay, by reducing it to a constant coefficient system. See, if you remember, constant coefficient systems are relatively easy, we can easily solve them, right? So if there is, let's say, if you can find out that there is some transformation which actually reduces this variable coefficient system to a constant coefficient system, then that is going to be very helpful, right? That is what this theorem actually, this decomposition does. Floquet theorem, this decomposition does. Okay, we'll see. Okay, so what is that? Let's look at the theorem there. Theorem. Let P of T and R. Okay, so what is P of T and R? P is W periodic, R is just constant non-singular matrix. Okay, you remember, we just did it here. You see, it's a constant matrix R and P is W periodic. Okay, so we are just assuming that. So let's say that those are the matrix such that we can write it, the fundamental matrix phi of T is nothing but P of T times e power RT. Okay, then the transformation, this is very important, huh? So you can have a transformation. What is the transformation? So let's say you are given a fundamental matrix, you can of course decompose it into Pt times e power RT. That is the Floquet theorem, right? Once that is true, then the transformation, this transformation, what is it? Y of T given by P of T times W of T, okay, reduces the system. What is the system? X prime equals to AT times X to the system. You see, this homogeneous, see, once we know how to solve the homogeneous problem, we can of course go and use Duhamel's principle to solve the homogeneous problem, right? That is always done. So we just have to somehow work out the homogeneous problem. What happens is this, it's saying that you have a transformation. You can have this transformation. Y is given by what is it? What did I write? But anyways, I should write it as one second. I should write it as x maybe. Yeah, it will be better. So sorry, what is y? I have to write y in another case. So let's just write it as x of t. Let's just do it this way. Otherwise, I have to again go through that y is the solution of that problem. Anyways, reduces the system this to the system. What is the system? W prime equals to R of W. You see that the variable coefficient system actually gets reduced to a constant coefficient. Okay, so how do you prove it? Let's look at the proof. So since, see, phi is a fundamental matrix, so what is it? Then phi prime of T, we know that this is nothing but A of T times phi of T. Okay, and you see, if you look at that the theorem, this relation phi of T, and since phi of T is nothing but P of T times e power RT, then you see we can take the derivative, right? So you see, therefore P of T times e power RT, the derivative of that is nothing but A of T, right? And what is phi of T? It is Pt times e power RT. So it is Pt times e power R times T. Clear? What does that imply? That will imply that first of all it is P prime of T e power RT. This is from the first assignment we are using here, plus P of T e power RT, R e power RT, equals to AT times Pt e power RT. Is this fine? Now you see what happens is this, I can write it like this. It is p prime of t plus p of t times r minus at times pt, clear, times e power rt is going to be 0. Is this okay? Now you see, if you use this transformation, so basically what is this transformation? X is given by pt times wt. Okay, so using the transformation now, as x of t is nothing but pt times wt. Okay, so see x, why I wrote y there, so basically x solves this problem, right? Okay, so you take that solution x and then you write it as x equals to pt times w. That's what the idea is. Okay, so see, x solves this problem, right? So what happens, what I'm trying to say is this, p, so okay, let me do it this way. X of t is pt times wt, right? Wt. Okay, so what does that gives us? X prime of t is nothing but p prime of t wt and then p of t w prime of t. Here, now what does that imply? What is x prime of t? It's nothing but at times x of t. At times x of t. X of t is nothing but pt times wt. Clear? That is nothing but p prime of t wt plus p of t w prime of t. That's what we are going to get, right? Okay, so if you put everything together, see what we are going to get is this. That will imply that p of t and then w of t, okay, plus, one second, let me just check this part. P of t, w of t, w prime, no? P of t, w prime of t, sorry. Yes, and plus p prime of t, w of t, okay, one second, I did some mistake somewhere, I think. So this expression is there. Okay, this is p prime is there, right? See, p prime is there. Okay, yeah, fine. Okay, fine. Yeah, so this will imply that this is basically nothing but, it says that p of t, okay, and w prime plus, so w prime of t, that is w prime of t, sorry, w prime of t, so p of t w prime of t, this particular thing, plus p prime of t, okay, minus a of t p of t, okay, and times w of t. This is going to be 0. Yeah, that's what we are going to get, right? If you just write it to, if you just put it together, that's what you are going to get. This part we are just taking on the other side here. So it is p prime minus a times p times wt equals to 0. Yes, sorry, I just got confused a little bit. Okay, so now you see, let's call this as 1 and let's call this as 2. Okay, if you combine 1 and 2, you are going to get your result. So therefore, combining 1 and 2, okay, what we are going to get is your result, which is we have, you see, this is p prime minus a p, that is 0, right? So what happens is we have that w prime, see, p prime minus a p is minus p times r, right? So you just replace here the minus p times r, okay, so, and p is non-zero, P is a non-zero matrix. So basically it becomes y w prime minus r w equals to 0. That's what. Okay. So then that will imply w prime equals to r w. I hope this is clear. Okay. So hence proved. Okay. So what did we show? We showed that if you have sufficient, if there is if A is continuous and it is w periodic, then Floquet theorem says that you can just take this, break it up into a exponential matrix times a periodic matrix, a periodic matrix times the exponential matrix, and then using that you take a transformation which is x equals to p times w, and you reduce the original equation to a, which is a variable coefficient equation. Yeah, this is variable coefficient. You reduce it to a constant coefficient equation. Yes. Once you do it, now you see what happens is this. Let's say if I give you to solve this variable coefficient equation where A is nice, let's say all these properties are satisfied, is w periodic and everything. Then what happens is, if you can just break it up into this p times e power rt, then you can actually know what r is. You solve w prime equals to rw, which is easy to solve because this is a constant coefficient equation. This is e power rw times some constant, right? So you just calculate that. Once you get it, you get what the solution w is, you just put it with the p. So p times that solution will be your x of t, which satisfies the equation, and you are done. Yes. So with this I am going to end this video.